All right, my board's turned up then. So previous video I put up about DC protection circuits, just a few working principles. At the end of that video, I sort of brushed over a bit of a design I was working on for a DC protection circuit. Some aspects of that design have actually made it into this board, but yeah, here she is. I'll go over the actual final schematic I ended up with in a bit, but this is a Never Osh Park board. It's gold plated, which is much better if you're trying to do surface mount devices like this. I mean, you can see how tiny some of them are. Let's get a pen here. Let me look at these capacitors down here. If I can get the glare off the lens, they are, about the width of the nib of my pen here. So if you get tin plated, hot air sort of they sort of immerse it in a tin bath or something along those lines, and then basically a hot air blower blows the levels of the tin off. It's something like that to do. Anyway, it's lumpy. It's not smooth. You look at a tin plated board there; they're quite a lumpy thing. You want as smooth as you can get for surface mount. So this gold, that's immersed in a solution, obviously electroplated with a very tiny quantity of gold, but it makes for a very, very smooth finish. I messed up a bit with this board because when I was ordering, I saw the option for 2 ounce copper. Now, you'd normally go 2 ounce if you had a lot of high current. This is very low current. The actual relays and speaker, the current going to the speakers and the relays isn't on this board. This is just to drive the relays. So it didn't need to be 2 ounce, but I saw the option for 2 ounce and I thought, oh, yeah, I'll go 2 ounce. That'll be nice thick copper, make the board a bit stronger. Well, it turns out if you order the 2 ounce copper, it comes at the expense of some of the GRP they make the board from. So you can see that's very thin. If I get a Never Osh Park board, which I've had one, last one made with just 1 ounce copper, 1 ounce, 2 ounce, you can see the difference. So yeah. If you're ordering from Osh Park, bear in mind that if you want a nice strong board, go 1 ounce copper. 2 ounce is a bit flimsy. You see, I've got Molex connectors dotted around the board, so I'm going to have to be careful. Shouldn't be an issue, but I should just have to be careful, to make sure I support the board a bit from underneath when pushing them in, to make sure I don't damage the board. But yeah. Great service again, couple of weeks turned up, absolutely made to perfection, double-sided. The clearance around the polygon port, and is tiny. It sets 6mm clearance. It is absolutely fantastically made. So Osh Park, fantastic place to get your boards made. Highly recommend them. Right, so this is the DC protection board. Does differ slightly from the one I posted, and I should point out as well, obviously you can see on the board there's some capacitors, rectifier, regulators and stuff. So yeah, there's no smoothing capacitors, bypass, decoupling or anything shown on here, or power supply. It's just the operational side of the circuit. Well, I initially was going to use an op amp to take the outputs from each of the amplifiers and feed the signal into the detector circuits. Well, I was originally using a non-inverting type one. Now, if you don't know about op amps, basically they're just a standard high gain amplifier. You have 2 inputs, a non-inverting and an inverting. Well, basically the output will always go to the most positive input, and with a feedback network, the op amp will always try to keep the 2 input voltages exactly the same. So if you try the non-inverting side to 0V like I have here, then this terminal, as long as we're staying within the output swing available of the op amp, and it's the amount of current it can also deliver, so voltage and current obviously play a role in this, then this terminal here will always be at 0V. Well, I'll explain why we need to do that. If we look at, say, original design, say this was our 4 amplifiers here, each one going for a 100k resistor, 100k here. Well, if, let's say we're not even playing any music to keep things simple, These 4 terminals are all at 0 volts. This is at 0 volts. There's no voltage difference between this point and any of these points, so there's no current flows, no voltage is developed across any resistors. Now let's say a fault condition occurs on this amplifier. Well, I wanted a DC protection that will trigger it at a low threshold, about 200 millivolts. Well, what we have here is a potential divider network. You can see we've got 100k input impedance from our amplifier to our divider network, and then 4 parallel resistors to 0V, because remember these amps were all outputting nothing, so that comes to 25 kilo ohms. So we end up with a potential divider where the output voltage, which is what we want here, is only 0.2 the value going in here. So we would need somewhere near a volt. If we had a volt, let's say we had a 1 volt fault on this amplifier here, it would only show us 0.2 volts on here. Now, realistically, not a massive problem, because chances are most fault conditions you just get a full rail voltage output anyway. But the point was, in some bizarre conditions, which I have seen, I wanted an amplifier that will detect that. Well, this one won't suffer that problem, because no matter what is going on these amplifiers, this terminal is always at 0, because we're staying within the boundary of what this op-amp can do. So let's say in our argument, our example here, all of these were at 0 volts. This one developed a fault of 1 volt. Well, this was already at 0. The 1 volt's developed across here still. There's no voltage across any of these, so they're not giving any, they're not forming part of a potential divider network, because 0 voltage across them, 0 voltage, 0 current. So all the current is coming through here. So this went positive by a volt. The output went negative by a volt. This terminal stayed at 0V. So this means our detector can detect very low voltages indeed. And the other outputs from the amplifier can all be summed into the one op-amp input, and it won't affect the actual voltage being amplified on the output. Under that condition, obviously, as we start going through AC conditions, it gets a bit more complex. On the actual board, because I'm running a bridge-tied load amp, 2 of these resistors, one on, let's say I'm going to use the non-inverting side on each amp, are going to only be 47 kilo ohms. Reason for that being that if there is, let's say we plug something in and it's got a small amount of DC offset on it, it will make the inverting and non-inverting amplifier swing both positive and negative by the same amount. Well, that will still come across through these 2 resistors to sum to 0. So this op-amp won't actually have to do anything. So in that instance, there'd be 0 current flow through this resistor. So the op-amp wouldn't detect that offset, even though the speaker would have, it could essentially have a full rail-to-rail offset across it on both amps. And as long as they were both outputting an equal but opposing voltage, this would never see it. So by having one of the amplifiers a lower resistor, it then has a gain of just over 2. So if we have even just a 100 millivolt offset, if it's negative, this will see at 200 millivolts, it'll trip the DC protection. If it's positive, the exact same will happen. If there's an even and opposite output, it will still trip the DC protection circuit, which is handy. It does, however, mean, obviously, if only one of the amps goes into fault condition, that these ones will trigger at half the voltage of these. But either way, they still all trigger at a very, very low voltage. I could set this thing, because the way it works, I could set it to trigger it almost 20 millivolts, and I wouldn't end up with false triggering until I drop below the frequency I have set the detection circuits to operate at. I'll go into that shortly. Up here we have a loss of AC detector. So from our small transformer, 12 volt AC comes in. Its current is limited by this resistor. It can only pull this capacitor positive, it can't discharge it, so this capacitor charge is positive. Once the voltage, AC voltage, reaches its peak and starts changing in direction, there's no longer any forward voltage across this diode. It stops conducting. This capacitor slowly discharges through this resistor. As long as the next voltage peak comes up before this capacitor discharges below the voltage set by this resistor network here, this input will always stay more positive than this input. the output will stay more positive. This diode blocks it, so the loss of AC detector circuit won't activate the protection. It's only if we lose AC within a couple of cycles, the voltage on this capacitor will drop. This will trigger negative, and it will go to the rest of the detector circuit. Okay, this is the main side of the detector. First of all, I'm trying to figure out why I drew this. Look, it goes all the way up here, then comes back down again. I could have just drawn it across there and linked it. Hey ho, one of those things is you're moving your schematic about, you know, trying to tidy it up, you don't notice them, but yeah, the schematic's correct. It's just, that's a very random thing to do. So as you can see on the input here, if I have any more than 12 volts on any one of these at any one time, the output from this can't swing anymore, and the voltage on the non-inverting input will start to rise above zero. It would happen with 6 volts with any one of these. Under normal operation, it gets a bit complicated because obviously it's an equal and opposing signal, so it all affects what's going on. But it's irrelevant, basically, to protect the op amp and to stop. You know, if you go past the rail voltages, you end up with all sorts of strange operations. They no longer operate on the principle they were meant to operate on. So there's 2 small signal diodes here, and they will just keep this at plus or minus 6 volts above or below the 0V rail. As you can see, 600 millivolts negative and 600 millivolts positive will trigger these 2 diodes here. So that protects this op amp. These 2 op amps here, you can see this one is biased just slightly below the 0V rail. This input is biased just slightly above the 0V rail. So it's a very low threshold voltage. You can see 10k 120 ohm. It's way under a volt. These capacitors just smooth it out to, you know, stop noise getting into the circuit. So if the output from this amplifier goes above this threshold voltage here, which is very low, which as soon as the amps, it's basically as soon as we start playing any music on the amplifier, this is going to be swinging at a point where it's going to go higher or lower than these 2 voltages. So if it goes higher than this one, this op amp swings all the way up to the positive rail. If the output goes, where are we? Follows it down. If it goes any more negative on the inverting side than this network, this will swing up to the positive, try to swing up to the positive rail. If you notice, look, this one feeds the signal to the inverting side, this one swings it non-inverting. So even plus and minus, plus this swings positive, minus this swings positive. The opposite happens the other way round. If this goes more negative than this network, this swings negative. If this goes more positive than this network, this swings negative. You'll notice though, look, we've got 100k resistor, very low value, 180 nanofarad cap, and some diodes. Both of these diodes, when these swing positive, the only ways for the current to go is to charge up this capacitor. Same happens here, it charges up this capacitor. When the outputs swing negative, they start to discharge this capacitor, but they won't discharge it all the way down to the negative rail. We don't want that. We want it to, you know, ideally to not go any lower than the 0 volt rail. This diode keeps it no more than, well, no less, how you want to look at it, than 0.6 volts below the 0V rail. These are our timing circuits. The output from these 2 is fed to another 2 op amps running as comparators. This time you see they share a common voltage reference. It is it's about 2/3 or something. It's something about 9 volts, something around there. Basically, so if at any point these capacitors charge above about 2/3 the rail voltage here, it will trigger these op amps. Now, obviously, as we go up in frequency, we just get a lower and lower ripple on either of these timing capacitors. So obviously, it will charge a small amount, discharge a small amount, charge a small amount. It will stay at very low voltage. As we drop in frequency, it would start to ramp up and come down again, ramp up, come down again. This one will do the same, but on opposite cycles. So as this one goes up, this one is going down, and so on and so forth. If either of these is positive or negative long enough to charge above that rail voltage, well, positive obviously on the output, but depending on the input, then either of these op amps will trigger and they will go negative, because you see they're both inverting. So positive input equals negative output. When they go negative output, you can see the diodes start to conduct, goes up to the trigger pin on our 555, sets our 555 timer into motion, output goes high, the transistor turns off. If it's just a quick pulse, then this capacitor here, the 555 timer in this monostable mode, the timing of the output being high is 1.1 times RC. So it comes out to about 4 seconds or so, thereabouts. If it's a quick pulse, even just a 1 millisecond, it's still enough to trigger the 555. The relay will not be activated again and allow the speakers to connect to the output until this network has been charged up. If it lasts past the point this network charges up, because the trigger's being held low, the output just won't be connected. This transistor here, obviously, it needs the output of the 545 to go low to start sinking current through the base. This allows collector current to pass to the relay. Relay obviously is going to connect here, but it's external, so I've not shown it on the schematic. This diode and resistor, for when the relay disconnects, obviously it will try to pull the voltage at the collector of this transistor way down below 0V rail. When we get about 0.6 volts below 0V, this diode starts to conduct and the energy from the relay coil is dissipated in this resistor as heat, obviously the current through it, I2R, and the relay opens quickly and the speakers are disconnected. See, the loss of AC circuit, rather than trying to feed into the voltage sense points that the DC, the summing amplifier feeds into, it actually feeds into the voltage divider network for the upper op amp. If it swings negative, this op amp sees it the same as there being a positive output fault on one of the amplifier outputs. So obviously the operation of the circuit is the same. So yeah, and it's handy again, because if there's a fault condition, as we shut down, this loss of AC won't, interfere with the operation of the circuit. You can wire this up in a manner where the loss of AC try to pull, if I had this, if there was a negative fault and the loss of AC was feeding into this rail, and let's say it worked by, pulling it down the same way, it would, hang on, bear with me here. If it went negative on this pin, this output would go negative, this output would go positive. So you see, it would actually interfere with this, and it would stop this op amp from working. Strange things could happen again. If I was trying to toggle it into the output from this one, we could end up fighting the two outputs. They could cancel to zero. So it feeds into there. You can see there is a small capacitor it has to discharge. Well, 1 microfarad and 1 kilo ohm isn't going to take long at all. It's a few milliseconds. It worst case scenario, and away we're going to go. So yeah, that's the DC protection circuit. That's what's going to be on this board. I'm just going to see that I'm here and I've got some schematics printed out. I'm just going to touch on the amplifier schematic quickly. Right, so this is the amplifier. There's an op amp at the input that isn't actually part of the amplifying circuits. That's because the amp's going to run 4 amplifiers in bridge tied low to make stereo. So with some jumper pins on the board, I'll be able to select between inverting and non-inverting to get my 2 equal but opposed outputs, which I'll need to go across each terminal of the speakers so I get full bridge tied load configuration. Excuse me. Vertical channel MOSFET amplifier, 2 paralleled transistors for each rail. They're IRF540 IRF9540 in a source follower configuration. Rail voltage is going to be plus minus 25 volts. There's some additional rectification and smoothing on board to allow the driver stage to have a slightly higher voltage to allow me to get near rail to rail swing out of them, which you wouldn't be able to do without that, because you need to be able to pull the gate voltage somewhere sort of 6-7 volts above the rail voltage, the collector voltage there, to actually get the source to go to full rail output. If we start the input, we've got a RF filter. Obviously that's going to filter out any radio frequency noise. Keep the amp nice and quiet. It's got a 22 kilo ohm input impedance. This side, it's actually capacitive coupled, there's 100 kilo ohm here, so it's going to be slightly less than 20 kilo ohms. This is obviously just to stop, you know, you could end up with a random potential on here, and when you plug in an input, it could be seen as a small, well, a small DC offset here all the way along the amplifier equals a large DC offset here, which we don't want. Current mirror, degeneration resistors don't really degenerate it a great deal. They're more there just because it allows me to run some tracks under them on the board. It makes life easier. I thought, well, I might as well bung some resistors in there instead of jumpers. JFETs, I wanted to build a JFET amp here. You can see, look, TL072 is a JFET op amp. Just wanted to use a JFET input stage. JFETs are almost extinct now. No one really uses them anymore. It's very hard to get. I think there was like the 2N2701s or whatever they were a very well used JFET for small input stages. These are VHF or video input FETs or something along those lines. They'll work just as well. Not quite as well, but nearly as well. Current sink sets the current through the long tail pair, about 3 milliamps. Current sink for the voltage amplifier stage sets it about 6 milliamps. VBE multiplier, because contrary to popular belief, you do need to track the output temperature, the temperature of the output stage when you're using vertical MOSFETs, otherwise they will go into thermal runaway. Very easy to overcompensate, so some of the voltage potential is applied by just the voltage being generated through the current in the voltage amplifier stage going through this resistor. Drops the amount of voltage across the VBE multiplier, and therefore drops its, slightly lowers its I can't think of the word, temperature coefficient. So the amount of how many millivolts across it is dropped for every degree centigrade it rises in temperature. Standard single pole Miller compensation capacitor, 100 picofarads, just a small 100 nanofarad to bypass the VBE multiplier at high frequencies. Current limit on the VAS transistor, because let's say we was overloading the amp or momentarily short circuiting it and these diodes started to conduct. They'll conduct it about 9 volts between gate and this terminal here, so obviously it takes into account the voltage from gate to source and the voltage being generated across the source resistors. The current would only be limited by sort of 3 milliamps times maybe a gain of 100, so about 300 milliamps. You'd end up blowing things, so this limits it to 12 milliamps. Seeing as 6 will be getting pulled through here, you'll get 6 milliamps through these diodes, and if you shorted it in the opposite direction, well, the VAS transistor would be turned off. You'd just be getting 6 milliamps through these diodes. Standard 10 ohm 100 nanofarad Zobel network on the output. Not an overly complicated amp, but should perform reasonably well. So yeah, op amp, couple of resistor, Zener diode, capacitor, smoothing, voltage dropper network to get the power for the input op amp circuit. The board for this one I've sent off to be done at ITED Studios in China. It's going to take a while, but it's a fraction of the price of Osh Park. Seeing as I was going through Hole, I thought, well, I've used Osh Park for my main board. I'd use cheapo Chinesium for my amp board. It's a fairly robust design. It's not particularly fine tracks. I've not got a ground plane on it. It didn't need one. So yeah. Anyway, that's where I'm going with this. I just need to wait for the boards from China to turn up now. I've then got to get all the little parts in for the circuit board. Need to get a hot air gun and some solder paste. I've soldered surface mount before, repaired things with the soldering iron. It's all right, if you're only doing a few components, but when you've got a whole board to do, now I'm going to solder paste that, lay the components on and hot air gun them. So yeah, it's just time and money now, really. You know, I work shifts. I work 3 shifts, actually. We change every week, so it can be hard to find the enthusiasm at times to, you know, actually get up and do some bits and bobs. Sometimes I just want to fall asleep on the sofa or stay in bed all day, which is understandable. And then, you know, it's having the spare money, you know, things like this. Actually, these were 3 boards, come to about 60 quid. Well, transformers, transistors, aluminium heat sinks, power supply capacitors, they all add up. So, you know, if I had the time and the money, I would just bang things out constantly. But unfortunately, I have a boss that I have to please. I have a job I have to go to, and I have hours I have to work and bills I have to pay, which come before my own projects. So such is life. I'm not moaning about it. Just about every other person in this country is in the same boat as I am on that one. So yeah, anyway, keep watching, and over the, hopefully, maybe within a month or so, I should have something pretty much resembling a finished amplifier, maybe a bit longer. But thanks for watching, and thanks for listening to me waffle on again for far too long. These videos are only ever meant to be quick 10-minute ones. I assure you I don't love the sound of my own voice. I just get a bit carried away. So yeah, anyway, hopefully the next video will actually be me maybe soldering some bits on here or something, or yeah, I think I'd quite like it to be that, really. Some bits soldered on here and actually testing it, making sure it operates as it's intended to. So, yeah, anyway, thanks for watching.